Hey everybody, so this is chapter 3. I'm on slide number 31. I'm working problems, so if you want to look at the PowerPoint separately, you can follow me as I work through. So the problem on slide 31 describes the reaction. I went ahead and you should be able to take the words of the reaction and write out the balanced equation. If you haven't done that yourself, do that before you look at what I have. But essentially, we have our balanced equation. The question asks, if we start with 40 kilograms of both reactants, how much of the product, urea, which is one of the two products, how much will that form? Kind of have to just realize when you're reading a problem, if it gives you the amount of both reactants, that's like my bread and my cheese, those are always going to be limiting reagent type problems where I have to work the problem twice to get to the product. Now, I will say for some of you guys, there are shortcuts you can take where you cannot compare the grams of the compounds, but if you get to the moles, and you can think about the moles of CO2 and the moles of NH3 that I have in this reaction, I compare it to the 1-to-2 ratio, which is like the ideal ratio. Some of you, if you're good at looking at ratios and that kind of stuff, you can see which one's going to actually be the limiting reagent at an earlier point. Once you know which one the limiting reagent is, that's really the only one that you have to finish, because you know that that's going to give you the smaller answer, which is going to be the right answer. So there's no harm in finishing both of them and pick the smaller answer. If you do take a shortcut, make sure you show enough work. If it's a problem where you have to show enough work that you can actually tell, like if I'm looking at it, I can tell what you were thinking when you cut one of them off and finish the other one. But anyway, so if we work through this, the first step, I'm going to divide by the molecular weight of CO2, it's going to be 44 grams per mole. Then the ratio, 1 CO2 to 1 CO NH2 twice, the urea. And then the molecular weight of urea, if you add that up, that's 60 grams per mole. So that's my calculation for the first one. The second one, I'm going to divide by the molecular weight of ammonia, is 17. This time it's going to be ammonia is 2 to 1, so 2 NH3 is in the bottom, to 1 urea in the top. And then again, I use the molecular weight, 60 grams per mole. All right, so I do those two. I can punch those in my calculator pretty quickly. And I did in the very beginning, I went ahead and switched the kilograms and the grams before I set it up. You could do that as a first step right here, but that's just up to you as to how you want to handle it. So the first answer ought to be 54,500 or so grams. And then the second one is 70,600. So clearly of those two, the theoretical yield of this reaction is 54,500, which tells me that CO2 is the limiting reagent and the NH3 is what we call the excess reagent. Okay, so if this reaction goes to completion, I'll make 54,500 grams of urea. I will use up all the CO2, so the CO2, the amount left over will be 0, but I will have some ammonia left over. So the question is, how much ammonia will I have left over? There are, again, several ways you can do this, but essentially once I know what the limiting reagent is, that's going to be the value that allows me to calculate a lot of other things. So what I would want to do here is take the amount of CO2 that's reacting, and I'm going to do a calculation just like this one, but I'm going to go from the grams of CO2 to the grams of NH3. So essentially, I'm going from the grams of the limiting reagent, if it fully reacts. If I go to the grams of the other reagent, what I'm going to figure out here is how much of this reagent will react also. And if I know how much reacts, I know how much I started with, I should be able to subtract those two numbers to see how much is left over. So that calculation, again, I'm starting with my 40,000 grams. do my 3 steps. I'm going to set this up a little quicker. The first step, the molecular weight is 44. Second step, it's 1 CO2 to 2 NH3s. And then third step, the molecular weight of ammonia is 17. So that's the quickest version of the numbers. I type those in. I got 30,900 grams. So that's how much NH3 has to be reacted to use up all my limiting reagent. So this is what's reacted. 40,000 is my initial. And so now if I do 40,000 minus what I used, it's going to leave over what's left. So 40,000 divided by 30,900 means that there's going to be 9,100 grams left over of ammonia. That's the amount of the excess reagent that remains, which is what the second part of the question was asking on slide 31. All right, so now I move on. The next topic, which actually comes up a little earlier in the chapter, I believe, but honestly, I kind of like to get through all when we learn the mole math, I like to get through all those calculations and the reactions and everything all together. But when we look at chemical formulas, we want to be able to look at the formula, figure out what the percent composition is, which is like what percentage of the weight of a sample comes from each element. It's pretty easy if you're given the formula to figure out what the percentage of each element is. So on slide 32, if you look at that one, I think that slide is pretty self-explanatory. If you know what the molecular weight is, the percentage is going to be the weight of one element in the formula over the total weight times 100. So they show glucose. If you look at the molecular weight of glucose, is about 180. If you think about how much of that 180 came from carbon, there were 6 carbons, each one weighs 12, so 6 times 12 is 72. That's the contribution of the weight from carbon, so that's the part, over the whole is 180 times 100, that gives you a percentage. It's easy to go from the formula to the percentage. What's a little bit harder though is to go the other way. If you're given the percentages and you have to find the formula. So we're going to skip on to slide 33, where we're given the percentage of the elements in a compound and we're supposed to derive the chemical formula. Okay? Now, when you do this, the formula you're going to find is always going to be the empirical formula. Because the percentage is going to allow us to find the ratio of the elements to each other, but it's all, when we do this method, we're pretty much always going to find the simplified ratio, the lowest ratio possible, so that's going to be the empirical formula. Okay, so when we solve for the chemical formula using percentages, we're going to find the empirical formula, and then if we need to find the molecular formula, they're going to have to give us a little bit more information that we'll talk about in a few minutes. So the problem given, we have a compound is 74% carbon. It is 8.7% hydrogen and 17.3% nitrogen. Okay, and we know the formula has to be CXHYNZ, where we don't know what X, Y, and Z are, the subscripts that go underneath each element, so we need to solve for those. Now, if it was, C1H2N3, what that would mean is for every 1 carbon, there'd be 2 hydrogens and 3 nitrogens. So it's the ratio of the atoms in the formula. But if it's the ratio of the atoms, it should hopefully make sense that it would also be the ratio of the moles of atoms. Because again, if we just go to a higher scale in terms of the number of atoms, go up to Avogadro's number, 1 mole to 2 moles to 3 moles would still be the same overall ratio in terms of the atoms. Okay? So, point of that is, if we can convert our values into moles and then go from moles, figure out what the ratio is, that's going to be the chemical formula. So, what are we going to do? We're going to start out this problem. They didn't give us any amounts of the actual compound or the each element, so we have to kind of just make it up. So the easiest thing, like regardless of the law of constant composition said the percentages of the elements are the same no matter how much the compound you have. So we have to make up an amount just so that we have solid numbers to work with here. The easiest number to make up when you have percentages is if we assume we had 100 grams of the compound. So I'm going to start out and just say, let's assume we have 100 grams of the sample, whatever this compound is. Well, basically that makes it really easy. If I have 100 grams of the sample and it's 74% carbon, well, 74% of 100 grams is 74 grams. So by making that assumption, I can switch my percentages, just switch those straight into grams. And then once I have the grams of each thing, like I said, we've said several times with balanced equations, and in this case, you can't figure out very much stuff in chemistry doing ratios of grams. But if we switch things into moles, the ratios with moles works a lot better. So I need to change each of these elements into moles. So for each one, I'm going to divide by the atomic weight. So for carbon, I'm going to divide by 12. For hydrogen, I'm going to divide by 1. For nitrogen, I'm going to divide by 14. To change grams to moles, you always divide by the atomic weight or the molecular weight. So for carbon, you divide that, I think that is 6.17 moles of carbon. If you divide that, you're going to get 8.7 moles of hydrogen. And then if you divide that one, I'm going to have to do that on a calculator. 17.3 divided by 14. That's going to be 1.24. Okay, so at this point, if I can look at these numbers and if I can tell what the ratio is, then I could just write my formula down. If the numbers are kind of messy like these are though, I have one more step that'll kind of clean up this ratio so that I'll have like a whole number ratio that I can use. So what I'm going to do is I'm going to take these numbers, I'm going to divide all three of them by whichever one's the smallest. So of these three, the smallest one is 1.24. So I'm going to divide that number into all three. So I'm going to divide this by 1.24. I'm going to divide this by 1.24. And I'm going to divide this by 1.24. Okay? So when I do that, well, obviously nitrogen's going to end up being 1 mole of nitrogen. Hydrogen, I'm going to have to divide that one. Is 7.02. And then carbon is 4.98. Now, any of these that are really close to whole numbers, I can round off. So this one's basically 5, that one's basically 7, that one's basically 1. If they're all really close to whole numbers, I can just write my formula and I'm done. So for this one, it's going to end up being C5H7N, and then the 1 is understood, so you don't have to put that one. But the only extra step you might have, if any of these came out to be really close to like some number 0.5, if you remember when we learned the balanced equations, if you get the right ratio of everything but something has a 0.5 beside it, all you have to do is just go back and double all of them, and that'll make the 0.5 become a whole number or really close to a whole number, and then that'll be my ratio. If you look at all these numbers and one of them is really close to 0.33, then you recognize, oh, that's 1/3, and then you have to go back and triple all the numbers to get them to whole numbers. So the key is when you write your formula, it needs to be a whole number. Okay, all the elements need to be whole numbers. If you recognize a certain fraction, you just multiply by the denominator of the fraction, but you have to multiply all the values by that number so that you keep the ratio the same. Okay? Anyway, so that's it. This is my empirical formula. Now, anytime you do this method, it's always going to find your empirical formula. You'll occasionally work a problem that'll have one more step. It might say, let's see, 60. So the weight of this compound, if I add up the empirical formula weight, so like the molecular weight of this thing, but it's actually an empirical formula, it'd be 12 times 5 plus 7 plus 14, which is 81. Okay? If they told me in a problem that the molecular weight of this compound was 81, then that tells me, oh, this empirical formula is the molecular formula. Now, sometimes they might say the molecular weight is 162. Well, if it's 162, that's twice as big as my empirical formula weight, which means I would need to go back and double all these subscripts to get the real molecular formula. Because remember, the molecular formula it's the same ratio, but it could be a higher level. So it really could be C10, H14, N2, or it could be C15, H21, N3. As long as you keep the right ratio, the percentages would still be the same. So the only way that I would actually know, is this the correct molecular formula, or is it twice as big, or 3 times as big, or 4 times as big? The only way I would actually know that is if they give me the molecular formula and I compare it to the weight of the empirical formula. Excuse me, if they give me the molecular weight of the compound, and then I compare it with that. Okay, so I'm going to cut off here. We got a couple more problems on different things, and then we're done for the chapter.